All right, let's just dive right into this explainer. Today, we're mapping out the mathematical landscape of calculus to figure out exactly how we can find the absolute largest and smallest values of literally any given function. You know, whether you realize it or not, our whole world is governed by optimization, finding the very best, the highest, or the absolute lowest of something. So we're going to decode the mathematical language that makes finding all those extremes possible.
We've got a really solid roadmap today. We'll hit the peaks and valleys, check out the extreme value guarantee, map some local extrema, find critical points, walk through the problem-solving strategy, and wrap it all up with the Gold Rush application.
So, Part 1. The peaks and valleys. Understanding absolute extrema. Imagine you're staring at a really complex formula. It could represent absolutely anything. The question is, how do we find the absolute highest or lowest point of that formula without, plotting millions of points by hand? In the real world, whether we're trying to maximize a company's profit, minimize the raw aluminum needed for a soda can, or calculate the exact max height a rocket hits before gravity takes over, we need a bulletproof, mathematically reliable way to pinpoint those extreme values. We literally cannot afford to just guess here. We need certainty.
And that brings us to absolute extrema. Now, a quick heads up. An absolute extremum doesn't mean absolute value like you might remember from basic algebra. Instead, it refers to the definitive, undisputed highest peak or the absolute lowest valley on the entire domain we're looking at. Think of a function like a giant mountain range. The absolute maximum is the summit of Mount Everest, and the absolute minimum? That's the very bottom of the Mariana Trench. It's the absolute limit within a specific space.
But here's the catch. Some functions have a really clear absolute maximum and minimum, while others just don't. Take an unbounded cubic function, for example. It shoots off infinitely up into space and infinitely down into the depths. That means it has neither an absolute maximum nor a minimum. So, it kind of brings us straight to the rules of our landscape. If we want to find these points, we need boundaries.
Which perfectly transitions us to Part 2, the extreme value guarantee, and setting the rules of the landscape.
This right here is the extreme value theorem. Now in calculus, theorems are basically our bedrock. And this one? It is a total powerhouse. It guarantees that if we draw a strict continuous boundary around our search area on a graph, we will 100% unequivocally find a highest and lowest point. It's literally mathematically impossible not to.
But you've got to pay close attention to the wording here, because this theorem requires two very strict rules to actually work. First, the function absolutely must be continuous, meaning you can draw it from start to finish without ever picking up your pencil. Second, the interval must be closed and bounded. It needs a hard start and a hard stop, like from x equals 1 to x equals 5. If there's even a single tiny point of discontinuity, like a sudden break or a hole in the graph, or if the interval is left open-ended, well, that guarantee completely vanishes. Without these rules, the function might just fail to have absolute extrema altogether.
All right, let's move on to Part 3, mapping local extrema, exploring the hidden valleys.
I want you to think of this mathematical landscape like two mountains with a valley right in the middle. The peak on the right is obviously the absolute highest point on the map. But what about that peak on the left, or that valley tucked between them? I mean, even if a specific peak isn't the absolute highest point on the whole map, it's still the highest point compared to its immediate surroundings. And mathematically speaking, those are incredibly important features for us to identify.
We call these spots local extrema. A local extremum is simply a point that's a max or a min only when you compare to the points immediately surrounding it. It's basically the champion of its own local neighborhood. And these are incredibly useful to us. Why? Because, as we'll see in a minute, if an absolute extremum doesn't happen at the very edge of our map, at the endpoints of our interval, it absolutely must be hiding inside one of these local peaks or valleys. They're our prime suspects.
Okay, Section 4, Finding Critical Points. Fermat's Treasure Map.
To actually hunt down these local extrema, we need to locate what mathematicians call critical numbers. A critical number is just an interior point in the domain of a function where one of two things happens. Either the derivative of the function equals exactly 0, or the derivative is completely undefined. This definition is quite literally our treasure map, because Fermat's theorem formally states that if a function has a local extremum, it can only ever occur at one of these critical numbers.
We can actually translate this math into something super intuitive visually. Remember, a derivative measures the slope of a tangent line, right? So a derivative of 0 means the slope is perfectly flat, totally horizontal. which is exactly what you see right at the smooth, rounded peak of a mountain or the very bottom of a smooth valley. On the flip side, an undefined derivative visually looks like a sharp, jagged corner or a spike. At those sharp points, you can't draw a single flat tangent line, but they can for sure still be the absolute highest or lowest points in their local neighborhood.
But hey, there's a really vital distinction we've got to make here. Fermat's rule says if a local peak or valley exists, it must be at a critical point. But, and this is a massive but in calculus, a critical point does not guarantee a local extremum is actually sitting there. The big takeaway here is that critical points are just candidates. They're suspects in a police lineup. A function might flatten out, giving us a derivative of 0, but then immediately keep going straight up. Think of a staircase with a wide, flat landing. The landing is flat, making it a critical point, but it's clearly not the top or the bottom of the stairs. There's no actual peak or valley there.
Moving right along into Part 5, the problem-solving strategy, locating the absolute extrema. We have this amazing 3-step checklist that takes all this highly abstract calculus and turns it into a super simple, practical procedure. Step 1. We evaluate the function at the boundary endpoints, the literal edges of our map. Step 2. We calculate our derivative, find all the critical points where the slope is 0 or undefined, and evaluate the function at those specific spots. Step 3. We just gather all those numbers, line them up, and compare them. The largest number is our absolute maximum, and the smallest is our absolute minimum. It's a foolproof way to ensure we check the edges of our map and every single interior hiding spot.
And when we actually put this strategy into action, the results match our expectations perfectly. The critical points we calculated using the derivative line up flawlessly with the absolute highest and lowest visual values on the graph. It's honestly super satisfying when the math and the visual landscape are in total harmony like that.
Finally, let's hit Part 6, the Gold Rush application, real-world optimization. Let's apply this to history. Consider the production of gold during the absolute chaos of the California Gold Rush, specifically looking from 1848 to 1888. We can actually model the millions of ounces of gold pulled from the earth as a mathematical function over time. By treating those specific 40 years as our closed, bounded interval, we can use our derivatives and our critical points to hunt through the timeline and pinpoint the exact year that represents the absolute maximum output of gold.
And when we do, we see this massive peak in production in the early 1850s. The math accurately targets this historical explosion in production. It really goes to show that finding absolute maximums and minimums isn't just some boring exercise in academic theory. It's exactly how we can analyze and quantify the greatest economic booms and the most devastating busts in human history.
So, as you look at the data in your own life, your business, or your studies, ask yourself, where are your boundaries? Where are your critical points? What exactly are you trying to optimize? Keep those questions in mind and get ready for our next explainer, where we'll unpack another incredible tool, the mean value theorem, to unlock even deeper insights into these mathematical landscapes. Until next time, keep looking for those peaks.